Section 1 Introduction. We're introducing a new approach to how most neural language models, LMs, handle text generation tasks. Typically, these models predict the next word or token in a sequence in an autoregressive manner. They generate a range of possible next words from a fixed vocabulary based on the preceding text. The actual next word is then chosen using a specific decoding method, like greedy search or nucleus sampling. This process continues until a stop condition is met, such as reaching a maximum length or emitting a special end-of-generation token. Our approach, however, is different. Instead of generating new words, we propose copying segments of text from existing collections. These segments can vary in length, from single words to multi-word phrases. For simplicity, we'll refer to these segments as phrases, with a single word being a phrase of length 1. We create a contextualized vector representation for each phrase and store them in an offline index. During the decoding process, we retrieve a suitable phrase from this index and add it to the current sequence. In essence, we're replacing the traditional next word predictions with a series of copy and paste operations. We've named our model COG, short for copy generator, and it has several advantages. Firstly, it selects phrases based on their context rather than individual words from a fixed vocabulary, which could lead to more accurate representation and selection. Secondly, it can adapt to new knowledge sources without any additional training, as the text collection can be updated easily. This could be beneficial in scenarios like domain adaptation and data expansion, filtering. Lastly, it allows for multiple words or tokens to be generated in a single step, potentially reducing the total number of decoding steps and improving efficiency. We've conducted extensive experiments to test the effectiveness of COG. On the Standard Language Modeling Benchmark, Wikitext 103, COG significantly outperformed standard baselines in both automatic metrics and human evaluation. Furthermore, when we switched the text collection from the Wikitext 103 corpus to a domain-specific corpus, LawMT, COG still outperformed the baselines without any domain-specific training. We also found that when we increased the size of the text collection to the larger NWiki dataset, we saw additional improvements, again without any further training. In summary, our contributions are as follows. We've introduced COG, a new method that reimagines text generation tasks as a series of copy and paste operations from existing text collections. We've shown that COG can outperform standard neural language model baselines on existing language modeling benchmarks. We've also demonstrated that COG can adapt to larger text collections and domain-specific text collections without any additional training. Section Summary. In this section, the authors introduce a new approach called COG, copy generator, for text generation tasks. Unlike traditional neural language models, COG reformulates text generation by copying and pasting text segments from existing collections, allowing for more accurate representation and selection. COG also enables training-free adaptation to new knowledge sources and the generation of multi-word phrases in a single step, improving efficiency. Experimental results show that COG outperforms standard baselines on language modeling benchmarks and domain adaptation settings without any additional training. Section 2 Background. Neural text generation. We'll be discussing the concept of neural text generation in this section. This field can be broadly divided into two main categories. One is unconditional text generation, and the other is conditional text generation. Unconditional text generation, also known as language modeling, is all about creating a coherent continuation of a given text. In simpler terms, it's like completing a sentence in a way that makes sense, based on the words that have already been given. This is done by estimating the probability of sequences in the text, represented as p_theta, x. On the other hand, conditional text generation is about creating text based on a certain condition, represented as c. This involves estimating the probability of p_theta, x, c. This technique is commonly used in machine translation and summarization. In this paper, we'll be focusing mainly on unconditional text generation. However, the methods we discuss can also be applied to conditional text generation. The standard approach to language modeling involves generating text in a left-to-right manner. This is done by predicting the next word based on the words that have come before it. This process is represented as p_theta, x_0, n, equals prod_I equals 1, n, p, x_I, x_ less than I. The model used for this process usually consists of two parts, a prefix encoder and a set of token embeddings. The prefix encoder, often based on the transformer architecture, transforms any prefix into a fixed-sized vector representation. The probability of the next word being a certain word is then calculated based on this vector representation and the context-independent token embedding representing the word. The next word is chosen based on the probability distribution over the fixed vocabulary. This process is repeated until a certain condition is met, such as reaching the maximum length of generation. Section summary. Neural text generation can be categorized into unconditional and conditional text generation. Unconditional text generation aims to generate coherent text continuations given a prefix, while conditional text generation generates text based on a specific condition. In this paper, we focus on unconditional text generation, where the generation process involves predicting the next token based on the prefix using a transformer-based prefix encoder and token embeddings. The next token is selected according to a probability distribution over the vocabulary, and this process continues until a stop condition is met. Section 3. Copy generator. We're introducing a new concept called the copy generator, or COG for short. Unlike traditional language models that use a fixed vocabulary, usually made up of words or subwords, our COG uses a dynamic vocabulary. This vocabulary changes based on the source text collections available. Each item in this vocabulary corresponds to a text segment, which we'll refer to as a phrase, from the source text collection. It's important to note that all phrases are context sensitive, meaning the same phrases in different contexts are considered different. To give you a clearer picture, imagine we have a set of source documents. For each document, we can extract a phrase of a certain length, where the start and end positions of the phrase in the document are marked. We'll call all the phrases in the source text collection as P. Our goal is to select the best phrases that can form a coherent text continuation following a given prefix. To do this, we compute a contextualized representation for each phrase using a phrase encoder. This allows us to construct a phrase table. Just like traditional language models, during testing, COG also uses a prefix encoder to convert the prefix into a vector representation. We then measure the fitness of a phrase to the prefix by the dot product of their vector representations. At each step, we select a suitable phrase and add it to the current prefix. It's worth noting that the size of the phrase table can be quite large, even up to billions. To search over this large candidate pool, we pre-compute the phrase representations and use a search pipeline based on maximum inner product search. Furthermore, to accommodate situations where no suitable phrases are available, we also add the context-independent token embeddings from standard language models to the phrase table. Section summary. The proposed copy generator, COG, model differs from traditional language models by using a dynamic vocabulary that consists of context-sensitive text segments from the available source text collection. Each phrase is represented by a contextualized vector, and the fitness of a phrase to a given prefix is measured by the dot product of their vector representations. To handle the large phrase table, pre-computed phrase representations and a course-defined search pipeline based on maximum inner product search, MIPS, are used. Additionally, context-independent token embeddings are included in the phrase table to handle scenarios where no suitable phrases are available. Section: Ethical consideration. We need to discuss some ethical considerations. The text produced by our model, COG, may include segments copied from other documents. This could potentially lead to copyright issues in real-world applications. Therefore, we need to keep a few things in mind. Firstly, we must thoroughly check the copyright of the source text documents. We should avoid using documents that have strict copyright protection or contain private information. Secondly, it's advisable to clearly cite the original source, especially when the retrieved phrases are lengthy. Now, let's talk about the structure of our model. As shown in the figure, our model is made up of three main parts. 1. A prefix encoder that converts prefixes into fixed-sized representations. 2. A context-dependent phrase encoder that calculates the vector representations of the phrases in the source text collection. 3. A set of context-independent token embeddings, similar to those used in standard neural language models. The prefix encoder's job is to encode the prefix into a vector representation for predicting the next phrase. We view the prefix as a sequence of tokens and encode them using the standard transformer architecture with causal attention. Causal attention only allows each position in the input sequence to pay attention to its preceding positions. This means the prefix representation can be calculated incrementally as the generation progresses, which makes the inference faster. In more specific terms, the prefix encoder transforms a prefix of length I into a matrix. This matrix has dimensions that depend on the hidden dimension and the number of transformer layers. The computation can be described as follows. The next state of the prefix encoder is a function of the current token and the current state of the prefix encoder. We use the hidden state of the last token as the prefix representation. Next, let's discuss the phrase encoder. Given a set of source documents, the phrase encoder calculates the vector representations of all the phrases in the documents. Drawing from previous work, we create context-dependent phrase representations in the following way. For a document of length m, we first apply a deep bidirectional transformer to get contextualized token representations. Then, we use two MLP models to convert these into start and end token representations. For each phrase in the document that starts at S and ends at E, we use the combination of the corresponding start and end vectors as the phrase representation. The benefits of this representation method are twofold. 1. We only need to encode the document once to get all phrase representations. 2. We only need to store all the token representations instead of all phrase representations. Section summary. The paper discusses ethical considerations when using the COG model, highlighting the need to check the copyright of source text documents and to quote the original source explicitly. The proposed model consists of a prefix encoder, a context-dependent phrase encoder, and context-independent token embeddings. The prefix encoder encodes the prefix into a vector representation using the transformer architecture, while the phrase encoder computes vector representations of phrases in the source documents using a bidirectional transformer and MLP models. This representation method allows for faster inference and efficient storage of token representations instead of phrase representations. Section. Context-independent token embeddings. We want our system, COG, to not only copy phrases from other documents but also to have the ability to create output using individual tokens. This is particularly useful when there isn't a suitable phrase in the source text. To achieve this, we incorporate traditional context-independent token embeddings into our phrase table. These tokens can be thought of as single-word phrases without any context. Training our model, COG, involves breaking down the task of text generation into a series of copy and paste operations. At each step, it chooses the next phrase either from the source text or from the fixed token vocabulary. In essence, phrases serve as the basic building blocks for generating text. To train COG, we divide each document in the training set into a sequence of phrases. We use a greedy segmentation algorithm based on forward maximum matching for this. For instance, if we have a document with M tokens, our algorithm segments the document from left to right. The first I tokens are cut out as a phrase if they can be found as a subsequence in other documents and I is the maximum valid value. This process is repeated until all tokens are cut out. Some of the resulting phrases might be single tokens from the fixed token vocabulary if no suitable match can be found. Let's say a document has been split into N phrases. If the KTH phrase is copied from another document, we use the phrase encoder to extract its context-dependent phrase representations. If the KTH phrase is copied from the fixed token vocabulary, we directly retrieve the context-independent token embedding of the phrase. COG operates on a shared vector space of prefix and phrase representations. The representations of semantically related prefixes and phrases should be closer to each other, while unrelated ones should be further apart. We calculate the training loss for next phrase predictions using the info NCE loss within batch negatives. This loss function involves a mathematical expression that calculates the logarithm of the ratio of the exponential of the dot product of the prefix and phrase representations to the sum of the exponentials of the dot products of the prefix and all other phrase representations and the prefix and all token representations. To maintain the ability to generate at the token level, we also train COG with the standard token level autoregressive loss. This loss function involves a mathematical expression that calculates the logarithm of the ratio of the exponential of the dot product of the prefix and token representations to the sum of the exponentials of the dot products of the prefix and all token representations. Finally, the total training loss is the sum of these two losses. Section summary. The paper introduces COG, a text generation model that uses copy and paste operations to compose output. It incorporates both context-independent token embeddings and context-dependent phrase representations to generate text. The model is trained using a greedy segmentation algorithm and a training loss that combines next phrase predictions and token-level autoregressive loss. Section 4. Experimental setup. In this section, we'll discuss our experimental setup. First, we'll talk about the baseline models we used for comparison. We used three models: the transformer, KNN-LM, and Retro2. The transformer is a widely used model for neural language models. In our experiments, we fine-tuned the pre-trained GPT-2 model. The KNN-LM is a model that enhances a pre-trained neural language model by blending its next token distribution with a k-nearest neighbors model. Retro2 is another model that enhances generation by combining a static BERT retriever, a differentiable encoder, and a chunked cross-attention mechanism to predict next tokens. Since there was no pre-trained Retro model available, we trained it from scratch using the Wikitext 103 dataset. Now, Let's talk about the implementation details. All our source codes and the baseline models are based on the Hugging Face transformers package. To ensure a fair comparison, the prefix encoders in the transformer, KNNLM, and our model, COG, all use the same model architecture as the pre-trained GPT-2 model. This architecture includes 12 layers, 12 heads, and 768 hidden dimensions. For the phrase encoder in COG, we fine-tuned the pre-trained BERT base-cased model. We trained all models for 400,000 steps using 8 Tesla V100 GPS. For all models, we set the learning rate, dropout rate, and gradient clipping to 5E5, 0.1, and 1.0, respectively. Due to memory constraints, we set the batch size to contain 256 phrases. For the BERT model in the phrase encoder, we set the maximum sequence length to 256. For the GPT-2 model in the prefix encoder, we set the maximum sequence length to 512. Our proposed COG model contains a total of 248 million parameters from the BERT and GPT-2 models, while the other models contain over 124 million parameters. To enhance the efficiency of COG, we encoded all the documents in the source text collections offline. However, retrieving from such a large phrase collection presents significant engineering challenges. To address this, we used a two-step process. First, we used a document retriever to find the top K-related documents for each given prefix. Then, we collected their corresponding phrase representations for selection. We used a popular semantic matching model, DPR, and a vector search toolkit, FAISS, as the document retriever. This allowed us to recall documents that have similar topics to the prefix. We empirically set the value of K to 1024. COG can be used with both greedy search and nucleus sampling. For greedy search, COG selects the phrase with the highest fitness score at each time step. For nucleus sampling, we first obtain the next phrase distribution by applying the softmax function to the fitness scores of all candidate phrases. Then, we sample the next phrase from this distribution. You can find more details about the implementation in the appendix. Section summary. The experimental setup compares COG with 3 baselines: transformer, KNNLM, and retro. The baselines and COG are implemented using the Hugging Face transformers package with similar model architectures. Training is done for 400,000 steps on 8 Tesla V100 GPUs, with specific hyperparameters set for each baseline. COG uses a course-defined pipeline for document retrieval, employing a document retriever and vector search toolkit. COG can be used with both greedy search and nucleus sampling for phrase selection. Section 4.3 Automatic Evaluation Metrics. In Section 4.3, we discuss the automatic evaluation metrics we used in our study. For each document in our test set, we took the first 32 words as the starting point. Both the baseline models and our proposed COG model generated text continuations of 128 words based on this starting point. We followed standard practices and used greedy search and nucleus sampling, with a probability of 0.95, throughout our experiments. We evaluated our results using several metrics. The first is MAV, a popular, efficient, and practical automatic evaluation tool that aligns well with human judgments. It's often used to assess modern text generation models. In our study, we used the GPT-2 large model to generate the MAV scores, and we set the scaling factor at 2.0. The second metric, rep-n, measures the level of repetition in the generated text by calculating the percentage of repeated n grams. The formula for rep-n is 100 times 1.0 minus the ratio of unique n grams to total n grams. A higher rep-n score indicates a higher level of repetition in the generated text. The third metric, diversity, measures the variety in the generated text. It's calculated as the product of 1 minus rep-n divided by 100, for n values from 2 to 4. Texts with higher diversity scores are generally more informative. While perplexity is often used as a primary evaluation metric in language modeling, we didn't use it in our study because our proposed COG model doesn't calculate next token distributions over a fixed vocabulary. This makes perplexity comparisons unreliable. However, we did test the perplexity of the generated text using an external language model, and we've included those results in the appendix. In Section 5, we present our experimental results. We evaluated our proposed COG model and the baseline models in 3 different scenarios: standard language modeling, domain adaptation, and enlarged phrase index. In Section 5.1, we discuss language modeling on the Wikitext 103 dataset. In this scenario, we trained the models on the training set of the Wikitext 103 dataset and evaluated them on its test set. The Wikitext 103 dataset is a large collection of Wikipedia articles with over 100 million words, and it's commonly used to evaluate the performance of universal language modeling. Section Summary. In this section, the authors discuss the automatic evaluation metrics used to assess the performance of their proposed COG model. They use the MAV metric, which is based on the GPT-2 large model and measures coherence. They also use rep-n to measure sequence-level repetition and diversity to measure the diversity of the generated text. Perplexity is not used as a metric due to the nature of the COG model. The baselines in COG are evaluated in 3 different settings: standard language modeling, domain adaptation, and enlarged phrase index. Section Results. We've conducted a performance comparison between our proposed model, COG, and other baseline models on the Wikitext 103 corpus test set. The results, as shown in our table, indicate that COG significantly surpasses the Transformer and KNN-LM baseline models on most metrics. To be more specific, COG enhances the MAV score by 2.71% over the best baseline model, which is the Transformer with nucleus sampling. This improvement takes the score from 23.43 to 26.14. Interestingly, despite the known issues with greedy search potentially causing severe degeneration problems, COG with greedy search still manages to outperform the standard Transformer baseline with nucleus sampling. This is evident from the 2.58% improvement on the MAV score. This finding suggests that COG is more robust and less susceptible to the degeneration problem, which is an added advantage. We also compared the average time taken by different methods to complete the generation on the test set. Since the phrase representations in COG are pre-calculated offline, we didn't include its encoding time cost. The results, as shown in our table, reveal that COG maintains comparable inference efficiency with the standard Transformer baseline. This is because the phrases copied in COG usually contain multiple tokens, which means COG requires fewer decoding steps to generate text of the same length. In contrast to COG, which uses a coarse-to-fine search pipeline, KNN-LM performs a large-scale vector search at every decoding step. This results in a much higher inference latency for KNN-LM than for Transformer and COG, which aligns with previous research findings. To ensure the reliability of our evaluations, we also conducted a human evaluation with 3 native speaker graders from a third-party grading platform. We randomly selected 100 test prompts and provided the graders with 2 continuations, generated by COG and Transformer respectively, in random order. The graders were asked to decide which one was better based on fluency and informativeness of the generated text. In cases where the graders disagreed on the same sample, we asked them to discuss and make a final decision. As shown in our table, our proposed COG model significantly outperforms the strong Transformer baseline, indicating its superior generation quality. Section Summary. The performance comparison between our proposed COG model and the baselines on the Wikitext 103 test set shows that COG outperforms the Transformer and KNN-LM baselines on most metrics, including a 2.71% improvement in MAV score over the best baseline. COG is also more robust and less prone to degeneration problems. In terms of inference speed, COG achieves comparable efficiency with the standard Transformer baseline due to its use of fewer decoding steps. Additionally, human evaluation confirms that COG significantly outperforms the Transformer baseline in terms of fluency and informativeness. Section Case Study. To better illustrate how our proposed COG copycat generation model works, we've included an example in the paper's figure. This example shows how COG can generate text continuations that are both semantically coherent and fluent. For instance, during the second step of decoding, COG uses punctuation marks like quotation marks and periods from a preset vocabulary to close off the movie title, the man trap, and the sentence. Furthermore, in the 9th step of decoding, COG directly copies the name of the TV series, Magic Roundabout, from a related document. You can find more examples in the appendix. We also tested our model in a domain adaptation setting, where models trained on the Wikitext 103 dataset are tested in a specific domain. We used the English portion of the Law MT dataset, which is an English-German translation dataset for legal documents, following previous research. The memory of KNN-LM, Retro, and COG were built from the Law MT training set. We also compared the performance of Transformer models, with and without additional fine-tuning on the Law MT training set. Our results, as shown in the table, reveal that COG outperforms even the Transformer model that was further fine-tuned on the Law MT corpus. Specifically, COG scored 2.93% higher on the MAV score than the fine-tuned Transformer model. This suggests that COG can specialize in different domains by simply changing the source text collection. While KNN-LM scored higher in terms of diversity, COG surpassed it by 3.39% on the MAV score, indicating that COG generally produces higher quality generations. We also conducted a human evaluation on the law-MT corpus, which was set up similarly to a previous study. The table shows that most of COG's generations are better than a strong transformer baseline. This suggests that COG can outperform even a fine-tuned transformer baseline without any domain-specific training. Lastly, we tested our model in an enlarged phrase index setting, using a large text collection, the NWiki corpus, and tested baselines on the Wikitext 103 test set. The NWiki corpus is a large-scale collection of Wikipedia articles with over 3 billion words, which is significantly larger than the Wikitext 103 dataset. The memory of KNNLM, Retro, and COG were built from the NWiki training set. Due to hardware limitations, Retro used a subset of the NWiki corpus, over 6 million chunks. We also compared the results of transformer models, with and without additional fine-tuning on the NWiki corpus. Section Summary. The authors provide a case study to demonstrate the performance of their proposed COG model. They show that COG can generate semantically coherent and fluent text continuations, including retrieving phrases and named entities from related documents. In domain adaptation experiments, COG outperforms the transformer model fine-tuned on the law-MT corpus, indicating that COG can specialize in different domains by switching the source text collection. In an enlarged phrase index setting, COG performs better than the fine-tuned transformer baseline without any domain-specific training, using the NWiki corpus as a large text collection. Section: Results. We're going to discuss the results of our experiment. The data is presented in a table, and it shows that our model, COG, when paired with the NWiki memory, outperforms other strong contenders, including COG with Wikitext 103 memory. What's impressive about this is that COG doesn't need any extra training. This suggests that we can train COG with a smaller dataset and still take advantage of the additional information found in a larger dataset, in a sort of plug-and-play manner. We also observed that, similar to the domain adaptation setting, the KNNLM baseline model does improve diversity scores, but it falls short when it comes to the MAV score, scoring 23.39 compared to COG's 26.97. It's worth noting that the transformer model with fine-tuning performs slightly worse than the one without fine-tuning on the NWiki dataset. This is mainly due to differences between the NWiki and Wikitext 103 datasets. We also wanted to see how the size of the phrase index impacts the quality of the generated content. To do this, we randomly selected several subsets of the NWiki dataset, ranging from 0.1% to 100% of the dataset. As shown in the figure, when the proportion is less than 1%, COG's performance remains fairly consistent, which is to be expected since few additional documents are added to the phrase index. However, when the proportion exceeds 1%, the larger the phrase index, the better the quality of the content generated by the model. In the table, we can see the automatic evaluation on the test set of Wikitext 103, with the memory built on the train set of NWiki. The terms, transformer with FT, and transformer with OFT, refer to the transformer baseline model with and without additional fine-tuning on the train set of NWiki, respectively. The figure shows the quality of content generated by COG with different sizes of the phrase index. For each proportion, represented by a point on the x-axis, we sampled 10 times and recorded the average MAV score. A proportion of 0.0 means that only documents from Wikitext 103 were used. Section Summary. The experimental results demonstrate that COG with NWiki memory outperforms other strong baselines and COG with Wikitext 103 memory, even without additional training. This suggests that COG can be trained with a smaller corpus and leverage additional information from a larger corpus in a plug-and-play manner. Additionally, the investigation into the effects of the phrase index size reveals that as the proportion of the NWiki dataset increases, the larger the phrase index becomes, resulting in better generation quality for COG. Section: Dense Retrieval. We've been using the dense retrieval method extensively in various natural language processing (NLP) tasks, such as answering open-ended questions, facilitating open domain dialogues, and translating languages. Unlike traditional sparse retrieval systems like BM25 and TF-IDF, dense retrieval creates a shared vector space for queries and documents. In this space, a query and its relevant document are closer together, meaning they're more similar than a query and an irrelevant document. One study that closely aligns with ours is dense phrase. This research reframes the task of answering questions as a problem of retrieving phrases. In this approach, phrases are directly fetched and given as answers to factual questions. However, our goal is slightly different. We aim to generate coherent text continuations by retrieving phrases over multiple rounds. This task is more challenging because the connection between two consecutive phrases needs to be smooth and logical for the text generation task. Another area that's been gaining traction recently is retrieval augmented text generation. Most of the previous studies in this field have enhanced the quality of language models generation, for example, their informativeness, by basing the generation on a set of retrieved materials, like relevant documents. Our research follows this trend but takes a significant leap forward. Unlike previous studies that combine retrieval and generation, in our COG model, retrieval is the generation. Another contemporary study that aligns with ours shares the concept of replacing the fixed vocabulary with a non-parametric phrase table. However, this study focuses on masked language modeling, while our focus is on causal language modeling and text generation. Section Summary. Dense retrieval is a technique used in various NLP tasks, such as question answering and machine translation, where a shared vector space is learned for queries and documents to find relevant pairs. While dense phrase focuses on retrieving phrases for question answering, our work aims to generate coherent text continuations through multiple rounds of phrase retrieval, which is more challenging. Our work, COG, takes a radical step by integrating retrieval and generation, unlike prior work that combines them separately.